We're going to take a look at a typical memory problem relating to .NET's usage of unmanaged memory. In ANTS Memory Profiler, I'll select the application which I want to profile and ensure the Profile Unmanaged Memory option is enabled, so ANTS will collect this information. It's generally a good idea to take a memory snapshot once the application has loaded, so I'll do that. The application is reasonably straightforward. It reads a PDF document and lets you output a series of images to a folder representing each of the document's pages. We can see on the timeline that memory usage grows sharply now that I've opened that document. Nearly 1 GB feels like a lot of memory to be using for this task, so we may want to come back to why the memory usage is so high. I'll take a snapshot now in case we want to do that. I'll convert another PDF too. We can see a smaller increase in memory usage, which probably corresponds to processing the new document, which makes sense because this PDF is far smaller. But strangely, the large amount of memory associated with opening the previous PDF doesn't seem to have gone away, even though we're not using it anymore. It's definitely worth taking another memory snapshot to investigate this. Looking at the summary screen in ANTS, we can see an overall distribution of where memory is being used. In this case, it's almost entirely being used in this red unmanaged memory block. To get an idea of where that unmanaged memory is being used, we can take a look at the memory breakdown by unmanaged module. This shows us that almost all this unmanaged memory is being used by the mu-PDF module, which is responsible for PDF generation. This isn't too surprising in this instance, but when you're dealing with a larger application which does more things at once, this high-level overview can be really helpful. So we suspect there's a problem with how we're using the PDF library, but we need more information about what's really going wrong. If we switch to the class list, we can see a list of all the .NET classes which exist in memory. We can see how many instances of each of these classes exist, how much memory they're using, and how that's changed since the baseline snapshot. We can also filter this list based on useful properties of those classes, but crucially, as well as seeing the managed memory usage, we can also see how much unmanaged memory each of these classes are responsible for holding on to. I'll sort this list by unmanaged memory usage, and we can see this mu-PDF.NET class rises to the top, which is occupying most of the unmanaged memory. This class is a .NET wrapper which acts as the interface between our .NET application and the unmanaged mu-PDF library which we're using. It's worth noting that this class isn't using very much .NET memory, so it would be unlikely to catch our attention if we weren't able to look at unmanaged memory. So this is a great next step as we've narrowed the problem down to a .NET class, but we still want to understand why that class is holding on to memory even though the first PDF is no longer required. Let's use the instance list to see the individual instances of that class. We can explore into the object itself, and you can see the main thing it contains is a pointer to a place in native memory. If we select one of these instances, we can look at the instance retention graph, which shows us all the reasons why this specific instance is being held in memory. In this case, it's exclusively because it's held on the finalizer queue. So at this point, we've narrowed down our problem to unmanaged memory, then isolated it to the mu-PDF unmanaged module, identified the .NET class responsible, and understood that this is because instances of this class are being held on the finalizer queue. The next steps are to understand why it's still on the finalizer queue. Let's jump to our source code and take a look at the finalizer method for this object. This is a special method which gets run by the .NET finalizer when it wants to clean up unmanaged resources for .NET classes which are no longer needed. The .NET finalizer runs on a special thread, and we don't control when it gets run. Looking at our method, we have a few lines which look to deal with cleaning up resources, and then we're logging this fact. This logging statement is likely to be the cause of our problems. The finalizer can only run on a single thread, so if it gets stuck for any reason, it can't carry on doing its job. And because of that, it's absolutely crucial that we don't do anything which might risk blocking the finalizer. There's a good chance that this logging statement is blocking. Perhaps it was put in during debugging and didn't cause a problem then, but now an issue with a slow database is meaning it's taking a long time to execute. Interestingly, if we look back at ANTS where the application is still running, you can see memory use has actually fallen over time. It's very likely that we've just slowed down the finalizer rather than blocking it entirely. Gradually the finalizer's working its way through all the instances of the mu PDF class, and over a long period of time perhaps memory will drop all the way to 0. There are a few fixes available to us in this instance. The easiest is to try just removing the logging statement, which is probably unnecessary anyway. A far better solution would be to implement iDisposable, which avoids the danger of this sort of problem in the first place by causing us not to entirely rely on the finalizer. Now we've done that, I'll reprofile the application in ANTS using the one-click relaunch option and perform the same actions again. This time around, once I open the second PDF, memory usage drops right back down. Problem solved. Try ANTS on your own code today, and if we can help you with any questions, please do get in touch. Thanks for watching.